What is fire? What is it made of and how does it work? And what's the difference between blue fire and yellow fire? Let's find out. So, what is fire really? Well, let's start with our most simple explanations. First of all, it's something called a combustion reaction. And that means we're going to take two chemicals. One of them is going to be a fuel and one of them is going to be an oxidant. And for those of you studying a bit of chemistry, that means one of them is a reducing agent and one of them is an oxidizing agent. And typically that means oxygen from the air will be our oxidizing agent and our fuel will be anything that reacts with oxygen, which, as it turns out, is most things. So let's start with a nice simple kind of flame, and that means starting with a Bunsen burner. So a Bunsen burner has a connection from some source of methane gas, usually through a rubber pipe, into a metal chimney, and importantly, at the bottom of that metal chimney is a tap to let air in. So we can mix different amounts of air with our methane gas. And that's important because methane doesn't burn by itself. And of course, the air doesn't burn by itself, although it could do if things got hot enough, but that's a story for another day. So, some methane comes into our Bunsen burner, we mix it with some air, and of course that air contains about 20% oxygen. So we now have a methane-oxygen mixture moving up through our Bunsen burner. But even that methane-oxygen mixture won't catch fire by itself. We need to get the reaction started, and that means using something called activation energy. A fire lighter might use an electrical spark. So in this case, we're going to use that electrical spark to begin our fire, to begin our reaction between our methane and our oxygen. So that electrical spark is very high energy and it makes our molecules very hot. They get so hot that they now move at very high speed and those molecules have enough energy to break up. This means that, number one, they can collide with other molecules and break them up. But crucially, these broken molecules make things called radicals. These are atoms and molecules that have unpaired electrons, and radicals are very reactive. Those unpaired electrons are looking for a partner, and they will take it from anywhere. And they will certainly charge into a molecule and rip the electrons out of that molecule, breaking up that molecule into smaller pieces. That molecule now has lots of energy and that will fly around, breaking up more molecules and creating more radicals. But crucially, this process takes energy. Energy is steadily lost to the surroundings as it gets spread out between all of these molecules breaking up. The next part of the process then is when these molecular fragments, these pieces of molecules and these radicals start coming together, meeting each other and making new low energy molecules. Things like water, things like carbon dioxide. Those molecules have very low chemical energy, and that means that they are going to lose the energy that they had to the surroundings in the form of heat. And the heat they give off is more than the heat that was needed to start the reaction. So that extra heat now makes more of those air molecules and methane molecules shoot around, break each other up, and creating even more radicals, which will then later recombine to make more low energy products and create even more heat in the process. And this is where the idea of our reaction zone comes from. Because we have our gas mixture coming up out of the Bunsen burner, then it meets a layer of hot breaking molecules, and the mixture coming out of our Bunsen burner starts breaking up on the inside surface of this reaction layer. But as they are pushed out, and they are pushed out by this stream of methane and air coming up through the Bunsen burner, they start recombining to give us our carbon dioxide and our water as the products, as well as a lot of extra heat. And this is our simple blue flame. And that blue color comes mostly from methyl radicals, which is CH3 with an unpaired electron, and hydroxyl radicals, which is OH with an unpaired electron. Then on the outside of the flame, we have our carbon dioxide, we have our water gas, and we have our hot air. So that's our most simple flame. What happens now if we add even more air, if we add extra oxygen, so we have more oxygen than we had gas? Well, now our flame divides into two parts. We have this hot, really bright cone in the middle. This area is very rich in methane. There's lots of methane fuel, and it's the hottest part of the flame. But just on the outside now, we've still got some methane left. But at this point, we've got lots of hot oxygen too. So this part of the flame is called the oxidizing flame. It'll add oxygen to anything because the oxygen is hot and it's angry and ready to react. So this is the flame that we use when we really want to make something hot, because we have all of this extra oxygen and all of our methane gets burnt very quickly in one very small space. So now that we understand blue flames, let's look at the slightly more complex case of the yellow flame. So now, as before, we have our methane gas coming up through the Bunsen burner, except this time there is no air mixed in there. So it's not until it comes out of the Bunsen burner that it can finally meet with some air and start the reaction. Now what we have is a very definite layer where the methane is meeting a layer of our hot reactive radicals, which is breaking up the methane itself into smaller pieces, into smaller hot reactive radicals. But now it's much harder for those radicals to find a partner oxygen molecule or partner oxygen radical. In fact, they have to almost wander about in this hot layer until they can finally meet up with some oxygen and create those low energy carbon dioxide water molecules, and now as well, crucially, lots of carbon monoxide, as the carbon monoxide forms temporarily before it can meet another oxygen atom and form carbon dioxide. And what this means is that those radicals have a lot more time to rearrange themselves. And in fact, what they will do is simply react with each other. And they start making longer chains of very carbon-dense molecules, mostly carbon now with just little bits of hydrogen hanging off the edges. And then those carbon-dense molecules, those carbon polymers, then start sticking together with other carbon molecules and making little balls of carbon now. And it's these little balls of carbon that we call soot. And this soot then heats up in the flame, and it gets so hot that it gives off this beautiful yellow light. Then, as it moves through the flame, most of that soot will react with oxygen and form our carbon monoxide and carbon dioxide, but some of it will escape as soot. That's our yellow flame. And in fact, it's very easy to see the structure of this flame. Here's a nice little trick that I got from Smarter Every Day. If you put a metal gauze over a yellow flame, you can see that it's hollow inside. So you can see that there is a zone where the gas is coming out from the middle, moving through the flame reaction zone before it gets to the outside in the form of carbon dioxide and water. At the bottom of the flame, you will see a blue zone where it's very easy for air to diffuse and meet the methane. That's very hot, of course. But what we can't see with the camera is that around the outside of the flame, there is also a hot blue zone, because at this point we have lots of oxygen and only a little bit of methane, so we can get our complete combustion and give us those methyl radicals from the blue flame. Now, a characteristic feature of the yellow flame is this flickering pattern. And this happens because diffusion is so important in a yellow flame. As the flame is burning up, remember, it takes much longer to burn that methane fuel because the air has to diffuse from the outside. So that blob of reacting methane now has time to get hot and to expand. And as it expands, cooler air from the surroundings can get underneath it and push it up. And that separates it from the flame underneath, and then it makes a blob of burning methane that slowly shrinks as it runs out of fuel. And then it's replaced by another blob of initially expanding hot gases underneath, which then also shrink as they react and run out of fuel. Okay, so now that we understand gas flames, now let's take a look at liquid flames, which are very similar but not quite the same. A liquid itself does not burn. What actually happens is that the liquid has a vapor above it, a vapor of molecules evaporating into the air, and it's that vapor which catches fire in a very similar manner to the gas flame that we saw before. So this case here is ethanol, and you can see the blue part of the flame at the bottom where there is lots of air diffusing in from the outside over the surface of the ethanol, and then there is the yellow zone at the top where we have a high density of ethanol molecules and a low density of air inside the flame, and therefore we don't get our complete combustion, and those ethanol molecules get stripped down to smaller radicals which can then recombine to make these balls of soot, which is what gives us the yellow color. But just as before with the gas flame, it's not a liquid that's burning, it's individual gas phase molecules. Now we can understand candles. The way a candle works is that the flame that we start with our activation energy starts burning the wick a little bit, and we'll talk about the wick and solid fires in a minute, but the heat from that flame melts the candle wax. That gives us a liquid, and then that liquid gets hot enough for the molecules to evaporate and give us our gas phase fuel. And other than that, the candle flame is very similar to the other yellow flames that we've looked at before. And once again, we have a hot blue zone at the bottom where the air can diffuse in very easily, and then a yellow zone further up. So a candle is just a a sequence of events. We have a melting of the wax to give us a liquid, then the liquid evaporates to give us our gas phase fuel, and then we have our reaction zone. So now finally we can understand wood fires. Wood fires have basically everything that we've looked at before, just more of it. Now, if you've ever tried to make a wood fire, you'll know that it's quite difficult to get them started. And that's because they need so much more activation energy. Now, remember that initial part of starting a fire, of breaking up molecules to make radicals and high energy particles, that takes energy. It spreads energy out. And it's not until those radicals start coming together to generate our products that they give off the heat, which generates more radicals and more heat. So if our initial bit of energy spreads out before it can make a large concentration of radicals, then our fire won't get started. So for that reason, we always have to start making our fire with very small pieces of fuel. And for this job, something in fact which is not wood is even better. Straw and grass seeds, things like that, are much better because they are high in a molecule called cellulose. And the thing about cellulose is that it comes with its own oxygen. So once we start burning it, it's very easy to keep it burning. Wood, however, has a lot of lignin in it, which is a much more complex molecule and is much harder to burn. But even then, our big problem is water. We have water inside wood very often, and if our wood is damp, it will not light at all, because the water is not going to generate any products for us with a lower energy. Water is already almost as low as you can go. So those water molecules will take the energy, they might even break up for a bit, but then they'll just recombine and they won't give us any extra energy. So for this reason, you've always got to make sure that your wood is good and dry before it will burn. So once we've done that, we build up our fire, use maybe a bit of grass, maybe use some seeds or something that will burn easily. In this case, we are using dry pine leaves, and they are full of oils which will evaporate quite easily and give us a nice gas that will get our fire started. Now we can build up with small pieces of wood and larger pieces of wood until we can get our fire hot enough to start burning our large logs. Now at this point we can see all of the things that we could see in our yellow Bunsen burner flame. Here we can see some jets of gas coming out from inside the log as the heat is breaking down these molecules of cellulose and lignin and generating gases that can burn quite easily. Now we also see the effects of diffusion pushing up our blobs of gaseous fuel and giving us the beautiful flowing shapes of the flames of a wood fire. Now in this early stage of wood burning, we are losing lots of volatile parts of the wood. We are losing lots of hydrogen, we are losing our oxygen, lots of nitrogen and other things. And this is actually a relatively cool flame, which is fine for a campfire or for cooking food. But as the fire continues, we lose those volatile parts, and those molecules that we've been breaking up, they recombine with each other to give us a very carbon-dense mixture of molecules now. The carbon is recombining with itself to make these long carbon polymers, and the wood steadily is reduced to almost a pure block of carbon. In fact, if we're very careful and if we burn our wood very slowly, we can burn off almost all of the volatile materials and leave just the carbon behind. And that's how we make charcoal. But now this remaining charcoal, this remaining carbon is so dense, it's difficult to break it up. But when it reacts with oxygen to make carbon dioxide, it releases a lot of heat. And what that means is it's difficult to start a charcoal fire, but once it's going, it's very hot and it lasts a long time, which is why we use things like charcoal for, of course, barbecues, but also for blacksmithing, for instance. So hopefully now you understand something about the chemistry of fire. But the conversation doesn't stop there. If you think about it, there is a connection directly to us as living things. Because if you're old enough to understand this video, then there are no longer any atoms in your body that you were born with. Just like a flame, you take in molecules of fuel and oxidant, and you rearrange those molecules, and then you expel them again. You are, in a very real sense, a reaction zone. You have a continuity of existence like a flame. You might look solid and continual as a flame looks, but just like a flame, you are a space that atoms and molecules move through.